All right, let's dive into one of the most critical challenges facing modern medicine today, antimicrobial resistance. In this explainer, we're going to unpack the clever mechanisms that pathogens use to neutralize our best drugs and look at how we're trying to stay one step ahead in this fight.
Here's how we're going to break it down. First, we'll look at the sheer scale of the global threat. Then, we'll get into the nitty-gritty of how bacteria actually resist antibiotics. After that, we'll cover how we classify these superbugs, and finally, we'll talk about the global efforts to prioritize this fight.
So, let's start with the impact. Just how big of a problem are we talking about? Well, the numbers really tell a stark story.
Look at this number. In 2019 alone, antimicrobial resistance was the direct cause of at least 1.27 million deaths across the globe. Now, to put that into perspective, that's more than the annual death toll from HIV/AIDS or malaria. It's a staggering figure that shows just how rapidly this threat is escalating.
So what exactly is AMR? This is a critical point. Resistance is a trait of the microbe, not the person. It's classic natural selection in action. Under evolutionary pressure, these pathogens develop amazing mechanisms to fight off our drugs, which makes treating infections incredibly difficult, or in some cases, impossible.
And this isn't just a problem in far-off places. It's hitting developed healthcare systems hard too. Take the US, for example. The CDC's 2019 data shows more than 2.8 million resistant infections every year, leading to over 35,000 deaths. That's a huge burden on public health.
So the big question is, how do bacteria pull this off? They've got a whole range of sophisticated biochemical strategies to neutralize antibiotics. It really is a molecular arms race, and we're right in the middle of it. Okay, so their playbook for survival really boils down to 5 primary strategies. They can chew up the drug with enzymes, change the drug's target so it can't bind, literally pump the drug out, block it from ever getting in, or hide inside a protective biofilm.
Let's take a closer look at that first one. Enzymatic degradation. A classic example is the production of beta-lactamase enzymes. You can think of these enzymes as molecular scissors. They find the beta-lactam ring, the key structural part of antibiotics like penicillin, and they just snip it, completely inactivating the drug. This table gives us a great side-by-side comparison. We've just talked about enzymatic inactivation, which includes big players like ESBLs and carbapentamases. Then there's target modification. Think of MRSA altering its penicillin-binding proteins. Next, we have efflux pumps, which are like tiny bouncers that actively throw antibiotics out of the cell. Then you have reduced permeability, where bacteria, especially gram-negatives, change their pore and channels to block drugs from getting in. And finally, biofilm formation, where bacteria create a physical shield that protects the whole community.
Okay, so with all these different defense mechanisms, we obviously need a way to classify these pathogens. We need a system to stratify the threat level based on just how many drugs a particular bug can resist. And that brings us to 2 key classifications you'll hear all the time, MDR and XDR. A multi-drug resistant, or MDR bug, is resistant to at least 1 drug in 3 or more antibiotic classes. But then you have extensively drug-resistant, or XDR bugs. These guys are resistant to almost everything, leaving us with only 2 or even fewer options for treatment. That's when things get really serious.
But it gets worse. Beyond XDR, we have the ultimate threat, pan-drug resistant, or PDR. These organisms are resistant to every single antimicrobial agent we have available. An infection with a PDR pathogen is, frankly, a nightmare scenario. It's a return to the pre-antibiotic era, where we have virtually no effective treatments. So facing this escalating crisis of MDR, XDR, and PDR pathogens, what's being done on a global scale? Well, this is where the World Health Organization has stepped in to lead a coordinated response.
The WHO created a really critical strategic tool called the Bacterial Priority Pathogens List, or BPPL. You can think of it as a most wanted list for superbugs. Its whole purpose is to focus the efforts of researchers, drug companies, and governments on developing new antibiotics for the bacteria that pose the biggest threat to all of us.
And this list isn't static. It's a living document. It was first published back in 2017, but it was just updated in 2024. They used a really sophisticated analysis framework and got input from experts all over the world to make sure the list reflects the most current data on which bugs are out there and what they're resistant.
So what does the 2024 list look like? It's broken into 3 tiers. The critical priority tier, these are the absolute worst of the worst. We're talking about gram-negatives like carbapenem-resistant Acinetobacter, which have sky-high mortality rates. The high-priority tier includes major threats like MRSA and VRE. And the medium tier has pathogens like drug-resistant strep pneumo, which we need to keep a very close eye on.
This quote really captures the gravity of the situation. Think about it. So many cornerstones of modern medicine, major surgeries, organ transplants, cancer chemotherapy, they all depend on our ability to control bacterial infections. As resistance chips away at that ability, the very foundations of medicine are put at risk.
Which brings us to the central challenge for all of us in clinical practice. Microbial evolution isn't going to stop. So the question is, how do we adapt? How do our diagnostics and our antimicrobial stewardship programs evolve to stay ahead of this relentless threat? Because developing rapid diagnostics and using the antibiotics we still have wisely, that is the defining challenge of infectious disease management in our time.